All right, let's talk about database indexing. So database indexing is a feature in databases that allows us to improve performance to facilitate the retrieval of data. Right? One naive way to retrieve things from data is to go one record at a time, looking for a particular set of fields that meet a particular criteria, and as we find those fields, we build a result set and then return them. I say naive because it's as naive as perhaps reading a phone book, from the first page all the way through, looking for a particular last name or a particular phone, right? It would be very, very expensive, very, very time-consuming to start from the beginning of a phone book, the very first item in a phone book, and just looking for the particular person that you were looking for. Yes, typically that's not how we consume a phone book. We assume that it's ordered in a particular fashion, and based on that order, we use an algorithm that can search through that same search space in much faster, much efficiently. Right? Typically, we can use start maybe in the middle and then half the times every single time. So indexing allows us to improve our performance. So for instance, if there's no, if you have imagine somebody gave you a phone book that is not sorted. Imagine having a phone book that is not sorted by last name. Then the only way to search for anything would be to indeed start from the very first person and visit every single element in there, looking for the last name that's of interest. Yes. Now, if somebody gives it to you, so we say that the performance complexity is proportional to the size of the number of elements that we're searching through, right? Just from algorithms. If instead somebody organizes it, right, and sorts it by, say, the last name, and if we're searching by last name, we can do binary search, right, and start in the middle and decide to go halfway through, right, so half. And this dramatically improves the performance to logarithmic performance, right? Logarithmic base 2. Or we can even do better, right? I mean, because we find that the problem with searching, right? The problem with the performance of searching is that you have to search, right? And that takes time. If we could organize our data in such a way that we don't need to search, then we can make the time that it takes us to search independent of the size of whatever it is that we're searching through. Right, so we can make a constant time search, so it's not dependent on what the size of the search space is. And we have analogies of this in real life, right? Many times our parents have come into our rooms, and they have found this huge mess in our rooms, and they yell at us saying, "How can you find anything in this room? It's just such a mess. There's nothing to find." But maybe in our own minds we have some kind of indexing mechanism that we know where everything is, right? And if they touch it, then we won't find it again. So it depends on who's organizing it. If this works, binary search works, only because we are meant to search it in a particular way. We're meant to search it using a last name, yes? And it's organized in such a way that it's convenient to search it by last name. But say we didn't have a last name, we had instead a phone number. Now the phone number, I know the data is in the phone book, right? That I know somewhere in the phone book my phone number's in there, and it would tell me who it belongs to. But it's not organized by phone, right? It's organized by last name. So even though it's organized, it's completely useless to me because I'm not searching by last name, I'm searching by phone, right? So if I have a phone, I'm going back to my linear search, right? I have to go back to linear search. Ideally, I would have maybe 2 phone books, Right? One that is organized by last name, and the other one is organized by phone, based on how I want to search it by. Yes? And that's exactly what an index is in a database. A database index, right, is just the same table, but perhaps organized in a different way that is convenient depending on how you want to search it. If you want to search it by last name, I'm going to index it by last name. If you want to search it by phone number, I'm going to index it by phone. Okay? Right? So you can have multiple indices on the same table, right, depending on how you want to retrieve the data. And how is it that you want to retrieve the data? Well, that's based on your select statements, right? Based on the select statements that you're going to be querying most commonly on a database, right? You want to index that database based on what the select statements, the where clauses, right? If you see yourself that you're in your where clauses, you have lots of usernames and first names or last names or salary or whatever, right? You would index your database based on those where clauses that you're using. Now we have multiple ways of organizing. Right? We can organize it by sorting the data, right? And if we sort it, we know that we can achieve some tree organization on breaking up the search space by half every time we narrow down whatever we're looking for. But we can do even better if we have a hash table, right, where whatever we are searching by, we're using it as the index itself. Okay, so for instance, if you had folks organized by their social security number, right, and you are selecting folks by their social security number, if it's organized, sorted. Well, I could just iterate, right, and say, well, I'll start in the middle, and then halfway. Binary search will tell me where that social security number is. But instead, if I use the social security number as I store it already in that position, right? I can use that social security number as an index into that array, and that object will be already in the place where I stored it. More or less like the analogy would be that you store things in your room. Everything has a place, and there's a place for everything, right? So that you don't have to search. Where is everything? Where it should be. There's no need to search. I know where it already is. That I put it there, right? And I know where I put it, right? So there's no search whatsoever. So databases use a combination of these two ideas, right? Of indexing. Using hash tables and tree-like structures like B+ trees, right? That to improve the performance of searching and retrieving data from a database. Okay. So here's the point I was trying to make earlier, that tables are just organized in one particular way. They can't be organized in multiple ways, right? Just like a phone book can only be organized in one way. It can be ordered by last name, or it could be ordered by phone, but not by both, right? You can have maybe two versions of the phone book, right? One that's sorted by last name, and yet another one which is a complete a copy of it, but sorted by phone book, by phone number, right? Based on how you want to search it. But you would have to have two different versions, each one sorted by or keyed by the different fields that you want to search by. Right, so there's only one way to organize a table. So you want to be able to have maybe different versions. But if you have different versions, then you increment the space that you need to store this data, right? Also, you increase your risk that the two tables or that the two data sets might become stale. One might become stale, and because which one is your master data? Right, which one has the real copy of the data, right? If you make a change in one of them, you would need to make sure that those changes propagate to all the other copies of the data set. Yes? So indexes. So indexes are, by definition, is a smaller version, an easier version of the original table, organized in such a way that it's easier to maintain. Right, easier to maintain. Perhaps it doesn't actually have all the data copied. Perhaps it only has the field by which it was indexed, and then a reference to where the original table lives, where the original record lives, right? So that you would need to make 2 hops, right? First, identify where the index is, the location, and then use a reference that would tell you where the actual record lives. And they're stored in a separate file, usually a separate file, and that contains the fields themselves plus some reference that allows you to navigate to the original record where they live. Right? To create an index, the databases provide this syntax. Create index, the name of the index. It needs to be a unique name. And then on the table and the field that you want to create the index on. Okay? So for instance, create index major IDX on the table student and the field major ID. Okay? Or, right, you could be on another field, like for instance a student ID. Right? And again, it depends your select statements what you find yourself searching by the most common searches, the most common select statements that you might find you might be using. So here's another index, right? We're creating a unique index. You can create a unique index on fields that are primary keys, such as SID. And we'll see what the difference is, right, between indices that are unique and indices that are not unique. Right? For instance, a unique index refers to a single row, right? Because that index, that primary key, by definition, is unique. Right? There's only one student who has primary key 10 or 20 or 30 or whatever. Yes? So whatever that index is going to have a reference to a single record, the original record, right? Okay. Whereas this the previous index, this major index, is not unique. This is not unique, right? Because if I index by major, there's going to be a whole bunch of records that have this same major. There's going to be maybe 1,000 students that are in one single major. Yes? Right, so this one major might have actually multiple references that reference multiple records. Right? Maybe it references 10, 20, hundreds, thousands of records, right, that have the same identical major ID. Make sense? Because multiple students are enrolled in the same college or the same in the same department. Okay? So let's contrast these two. Let's contrast the unique and the non-unique indices, right? We have the unique indices that we can create on primary keys or on fields that we know are unique but might not be primary keys, like for instance a username. We know it's going to be unique. Maybe we're not using it as a primary key, but it's unique. Right? So I could create, if I find myself doing a lot of select statements where username equal whatever, right, then it would be very appropriate to create an index on the username. Yes? And it's unique. It's a unique key. It references a single record on the other side. Whereas a non-unique, right, an index, a particular value might reference multiple records in the original table. Graphically, we can illustrate it this way. Right? A unique identifier, right, we create an index here. It takes the primary keys, 1, 2, 3, 4, 5. There we go. Right? These are the original records. This is the original table with a primary key, student ID, a student name, year of graduation, and the department, the major ID, where they're enrolled. 30, 20, department 30, department 20. In a unique key, a unique index that I would create would look like this, and it would have a reference. It would have a reference to the original record. Right? It would have the value of the index, right, and it would reference the original. Notice that in a unique index, it references one record. It makes sense, right? Whereas a non-unique index, right, you could have multiple records, multiple indices that refer to multiple records in the original table. Right? So, for instance, 10, the value 10 actually appears in multiple places in the original table. Right? It appears 1, twice, 3 times. Right, so if I do a select on telling me, tell me those users whose major ID is 10, it would come back with 3 records, not just 1, right? We will see in a minute that queries on unique indices are much faster performance, right, than queries on non-unique indices, right? We'll see that the performance can suffer quite dramatically when we use non-unique indices, and we'll see in a minute why. So underneath it, B trees is what is used to organize and sort and order these indices.